So hello everyone, this is lecture 4 for the electricity and magnetism. In the last lecture we have introduced the Gauss law and we were discussing some applications. We have discussed this thing with thick dielectric sphere and we have considered some cavity and it is symmetrically made inside this sphere. Now let's see the case. If this cavity is not symmetrically made, it can be anywhere in the inside the sphere and it is spherical in nature, this symmetry or this cavity also. So this is a dielectric sphere and there is spherical cavity inside this sphere. It can be anywhere and we need to find the electric field inside this cavity at point P. So now how can we find? See, it is given that rho is constant, means this charge density is uniformly distributed all over the sphere. So we'll assume that rho is also inside this also. So to make this 0, we need to assume that there is this minus rho density also inside this cavity. Only then this rho is always same everywhere, and here to make 0, minus rho should be there. So rho plus minus rho will give you 0. So that's why we assume minus rho here inside. Now we can just find the electric field due to this first sphere with rho density and due to this minus rho. Then we can just add them because of superposition principle. We can add them individually. So that will give you total electric field. So for this complete sphere, we already know the result at if this is the r positive, if we assume this distance and the vector. So at P point, it will give you this result. At any r distance inside a solid sphere or dielectric sphere, we have this rho r divided by 3 epsilon naught. So for this positive one, it will be rho r 3 epsilon naught. Okay, now this is for the E positive. Now because of this negative, again we can this vector as assume as r negative, this one, and this is B, and this is the vector between the origin of first original sphere and the cavity sphere. So this is r negative, so it will give you again same result, rho r negative divided by 3 epsilon naught, and this density is, this time is minus rho. So you have E rho and E minus rho, so you just add them. Vector addition will give you total electric field at this point P. So it will be adding of these. Now it will give you r plus minus r minus. So this r plus r minus will be equal to B vector. How? Because this r minus is equal to r plus minus r minus B. So it will be r plus minus r minus will be equal to B. So that will it equal to B. So total electric field at any point inside its cavity P due to this dielectric sphere will be equal to rho by 3 epsilon naught B vector. So I hope you understand this thing. Let's now as we find it this value inside the dielectric sphere at any r. So if this is in cylindrical symmetry and we need to find at any point inside, that how can we find that? So let's take a cylinder. So let's see that we will use the Gauss law. First we know this is sphere, means we have this cylinder symmetry. There is one curved surface and this circular surface. So direction of area will be n cap and this r cap. So in the now see the electric field will be in this direction only. So the flux E dot n will give you 0 here for this surface and flux for this will be 0. So flux will exist only for this surface. So we can just write electric field for this surface is E r cap, and the surface direction, the area element direction will be r d phi dz r cap because of cylindrical symmetry. Now this r cap will give you 1 and this r d phi will give you 2 pi, and it will give you means this will equal to, according to Gauss law, total charge divided by epsilon naught. So if charge density is lambda, so at the L distance it will give you lambda L divided by epsilon naught. Now this equal to this, and this r cap will give you 1, and this r d phi dz will give you 2 pi because of d phi and rl. Okay, so this L is due to dz, integrate dz, it will give you L, and 2 pi due to phi, d phi, and r is as it is. So this will equal to lambda L by epsilon naught, and this will, when you cancel out, will give you E equal to lambda by 2 pi epsilon naught r cap. So this is the same result we have already find for the Coulombs also using the Coulombs law. So this is true. Now we need to find the electric field at any point inside this. If we assume this is a dielectric cylinder, then we need to find inside, and uniform density rho, then how can we find? So let's we need to find this at this P point, and this is a infinite long cylinder. So uniform charge dielectric cylinder of radius r, and it is very long. So we need to find the electric field at this point. So we will make a cylinder at this point. Now how can we find at this? So it will be electric field will same as for any of the surface. So E 2 pi RL, because of these surfaces this will be 0 because direction is perpendicular to electric field. So E 2 pi RL, this surface will give you total charge divided by epsilon naught. Total charge will be density is rho multiply volume element is r dr d phi dz for the cylinder. This will give you total charge divided by epsilon. Using the Gauss law we are doing this. So d phi will give you 2 pi and dz will give you L. So this will be 2 pi RL dr. So rho 2 pi R L dr will give you your total charge. Now see, rho is constant, so take this outside and it will be 2 pi L. R dr will give you R square by 2. So after cancelling some terms which will cancel out, so E will be rho R divided by 2 epsilon naught R cap. So this will be the electric field at any point P, okay, with R radius of this small cylinder. Now if we take this rho is not constant, means it is non-uniform, and then we assume that rho is equal to kr, then just in place of this it will be kr and it will give you R square, it will be R cube by 3. So in the last you will get electric field as kr square by 3 epsilon naught R cap for the non-uniform, and this is for the uniform. So you must remember these results, very important. Now there is this planar symmetry, there is this plane seat we have, and this is infinite seat. And from the Coulomb's law we already find the electric field for this kind of structure, that was sigma by 2 epsilon naught n cap, but we need to prove this from the Gauss law also. So let's assume a cuboid, and this thickness is very small, means this is half downside of the seat and half is upside of the seat. This kind of structure it is. Now we need to find, so again the area element direction will be perpendicular, so only the flux will be given by this surface and this lower one surface, not from this surface, because these are only making the E dot dA, otherwise it will be perpendicular for this and this one. So that's why this and this lower one surface will only give the flux. So EA plus all the 4 will be 0 equal to total charge from this, if this area is A and charge density is sigma, so sigma A divided by epsilon naught. So this will be equal to E equal to sigma by 2 epsilon n cap. So this n cap, this is giving the same result as we find it from the Coulomb's law. Now let's see the definition, means the practical use of differential form of Gauss law. So we know differential form is divergence of E equal to rho by epsilon naught, where rho is charge density, E is electric field. So if electric field is given, this is example, if electric field is given kr cube r cap in spherical polar coordinates, you need to find the charge density, then you need to find the total charge contained in a sphere of radius r centered at the origin. So how you can find the rho? So see, you already know E is given, so you can find rho equal to epsilon naught and this divergence of E. So if E is given, you can find the divergence from the divergence formula for the spherical polar coordinates. This is 1 upon r square del by del r square and this E. So kr cube will give you this. So this will be divergence and multiplied by epsilon naught. This will be value of charge density. Now you have charge density, this is your first answer. The second you need to find the charge. So charge is nothing but rho d tau. So this is volume, and d tau for the sphere, for this sphere it will be 4 pi r square dr, and this rho is already find it, we already find this. So now integrating for complete sphere 0 to r, this will give you 4 pi k epsilon naught r5. So this will be your total charge. Now see, you can also use here the integral form of Gauss law. How can we do that? If you need to find a total charge, okay, so you can use this formula. Total charge divided by epsilon naught equal to flux. So E dot dA, E is given, and you know area element will be r square sin theta d theta d phi r cap, and E already given. So you can directly use this formula to find the Q enclosed, total charge enclosed. You don't need to find the charge density first. So that's how you can do that if this E is given and you know the area element. So let's start a new topic, that is electrostatic potential. So what is electrostatic potential? It is the same thing as we did in the classical physics. So it is the amount of work done to bring a charge from infinity to at any point, that will be given by electrostatic potential. So work is given by, let's say we need to go from A to B point, then total work will be given by E dot dl. So A to B, E is we know, this will be equal to Q upon 4 pi epsilon naught r square r cap. So for any vector r, electric field will be given by this Q upon 4 pi epsilon naught r square, where this r is the distance for this point. And you know dl element, so if we are writing in the spherical coordinates, so we can write dl as dr r cap, r d theta cap, r sin theta d phi cap. So when you do the dot product, it will give you only this r cap term. So this will be 1 upon r square dr, and you need to integrate for ra to rb. So it will give you 1 upon ra minus 1 upon rb. So E dot dl is equal to this. Now see, if we take the closed loop, means ra to ra, so this both ra rb will be equal to each other. This will give you 0. So A dot dl will be equal to 0 for the closed loop. Now see, if this is a closed loop, so we can, if this is equal to 0, we can also write this line integral into the surface integral using the Stokes theorem. This will be equal to del cross E dA. So this will also equal to 0 for the closed loop, and that means del cross E equal to 0. So what does this represent? If this is equal to 0, that means E is conservative in nature. So when this E is conservative in nature, that means the work done will be independent of path taken. It will be depending on the extreme and the initial position, and for the closed loop it will give you 0 always. So that is the meaning of if E is conservative in nature. Now see, if del cross E equal to 0, then you can assume E as a gradient of some scalar. So we assume E equal to del V. Forget this negative sign, we assume this E as some gradient of some scalar. So because del cross del will give you 0, that's why we can assume E as some gradient of some scalar, so del V. Now we assume this scalar as potential, so we need to put this negative sign. Why? Because this is convention, so that we get positive potential for the positive charge. We will see the example of this, don't worry about this. So that's why this is just the convention to get the positive potential for the positive charge. So this is the expression for the electric field in terms of potential. So from here we can find V will be equal to minus infinity to R at any R point, it will be E dot dl. So potential will be equal to this. At infinity we assume the potential is 0. So if you need to find VB minus VA, so how you can do that? So at VB equal to infinity to B and VA will be infinity to A. Now take the minus common, it will give you infinity to B plus it will be minus, then you can reverse the limit, it will be A to infinity. So you can write A to infinity and infinity to B as A to B, E dot dl. So that's how you will get this expression as this. So this is the general result for potential between A to B. If you are going A to B, then you can write that potential in this term. Okay, so let's take an example. You need to find the potential at this P point, and this is at R distance away. So E will be Q by 4 pi epsilon naught R square, R cap, and potential is given by this expression. So E dot dl, now E dot dl will give you this is R cap, and Q by 4 pi epsilon naught R square. So this dl is also in the same direction, that's why we are getting R cap dot R cap as 1. So you are just taking potential at this point, means you need to take the unit charge from infinity to this point. So this will be infinity to R, 1 by 4 epsilon naught Q by R square dr. So this integration will give you minus 1 upon R here. So you will get the final potential as positive. So that's why we have take this negative sign outside, so that when we solve this for the positive charge, we get this potential as positive. Okay, so that was the reason why we took the negative sign. I hope you understand this thing now, so that we can get this potential for the positive charge as positive. Now see, this potential is depending as inversely on the R power 1, but electric field is depending as the R power 2. So you must remember for this result, the electric field is depending on the R square, and potential for the single charge depending on the R power 1. Now if there are multiple charges and you need to find the potential at any point, so these are the positive charges, so it will be just sum of individual potentials due to each charge. So it will be for Q1, it will be Q1 by 4 pi epsilon naught R1, distance is R1. For Q2 it will be Q2 by 4 pi epsilon naught R2. So you can just write a summation in the general form. This I is going from 1 to n, it will be Q1 divided by 4 pi epsilon naught R1, Q2 by 4 pi epsilon naught R2. That's how you can take the total sum. That will give you total potential at the point, this point. Okay, now if this charge distribution is not discrete and this is continuous, so you have some body in which the charge is continuously distributed, then this will change to integration, and here it will be dq. So this will change to this V equal to 1 by 4 pi epsilon dq by R. Now you can see this dq can be, if you have a solid volume closed surface, then dq can be given by rho d tau, and if it is a surface of 2D, then you have the surface area, it will be sigma dA. Surface charge density you can use, and for the length 1D, so you can use the lambda, that is linear charge density, surface charge density, and the volume charge density. That's how you can find the dq value, and you can integrate to get the total potential. So see this, and here we assume this condition that for the continuous charge, if you take at any point which is far away from this continuous charge, then potential must be tends to 0. Okay, so V tends to 0 for the far away from the charge distribution. So that's it for today. Thank you everyone.